In this video, we are going to continue our work with expressions and writing expressions with variables to represent a situation. All right, so we should be on page 641. Here is a 3x3 square surrounded by tiles. Without counting one by one, how many border tiles are there, meaning the blue ones? And explain how you knew without counting. I will pause so we can discuss. All right, now let's talk about if there's a 5x5 tile. How many green tiles would there be without counting one by one? I will pause so we can discuss. All right, let's keep moving along. Take a look at Lucia, Kyrie, and Manuel's expressions for the 5x5 square. How are all of their expressions alike? Let's look at Lucia's square. She has 4 red lines that are each 5 units long. So that would be the 4 5s. Each of these 5s represents the red. And then each of the black dots represents the 4. We have 1, 2, 3, 4 black dots. All right, now let's look at Kyrie's line, or expression, I should say. She has 4 times 5 plus 1. So this 4 represents the number of lines. And then the 5 plus 1 represents the length of each line, because each line is 6 units long if you count them out. So she has 4 units that are each 5 plus 1. The 5 is the length of each side, and then the 1 represents the one on the corner. Manuel has 7 and 7 plus 5 plus 5. 7 and 7 each represent the black lines. The 5 and 5 each represent the blue lines. All right, let's talk about how are all these expressions alike. Well, first off, they count out the number of each of the border tiles of the green tiles. Number 2, they all equal the same thing. If you do 5 plus 5 plus 5 plus 5 plus 4, that equals 20. Sorry, 24. 5 plus 1 is 6, times 4 is also 24. 7 and 7 is 14, plus 10, 5 and 5 is 10, also equals 24. So all of those expressions count out the number of tiles, and they all equal 24. In other words, they are all equivalent, meaning they have the same value. All right, let's keep moving along. So equivalent expressions, they look different, but have the same value. Here are 3 new squares. Determine the number of border tiles for each square. All right, so let's go back to here. I'm going to look at Lucia's expression. She knows that there are at least 4 lines of 5 because it is a 5x5 square, and then there are 4 tiles on each corner. Let's apply that to the 6x6 square. We have 6 on each side. So let's write 6 times 4, because there are 4 groups of 6. And then there's going to be 1 on each corner. I'm going to switch to red. So 6 times 4, and then add the 4 red. Let's apply that now to the 9x9 slide. We have 4 groups of 9, because there are 9 tiles on each of the 4 sides, but then we have to add in the 4 extra corner tiles. Let's apply that to the 10 by 10 square. We need 4 groups of 10 because there are 4 sides each that have 10, and then add in the 4 border tiles, or the corners, I should say. All right, how can you determine the number of border tiles for an n by n square? Meaning any number of tiles. Let's look at the expressions that we wrote. For each expression, we multiplied the side length times the number of sides, and then added in the corners. Let's apply that to n. If n is the side length, we're going to use an n times 4 sides, and then we're going to add 4 for the corners. So that would be for any number of side lengths for n. If it was a 12 by 12, we would say 12 times 4 is 48, plus the 4 extras for the corners would be 52, and so on and so on. Any number of sides plus times the 4 for the 4 sides, add in the corners. We can also rewrite this as 4n, or n times 4, plus 4. N times 4 is the same as 4n. We cannot put these together to make 8n. We're going to talk about that later, but since one has an n and one does not, you can't put them together. All right, let's keep moving along. Manuel wrote the expression for the number of border tiles in an n by n square. He has n plus 2, and n plus 2, plus an n, plus an n. Show how Manuel's expression is connected to his sketch. All right, so let's look at the n plus 2. There are 2 of them. Where do we think that there is a length and then add 2? That is correct. That is going to be the black lines. Each of the black lines represents n plus 2 because we have the side length of n and then 2 extra squares, so n plus 2. And then each of the ends, again, is one of the side lengths. Remember, with a square, all the sides are equal, so each side length of the square is represented by n. We don't know what it is, we just know that it is n. So each n is one of the blue lines, the black lines are each n plus 2. That is how the expression is connected. All right, let's keep going. What might Kyrie's sketch be for the number of border tiles for an n by n square? All right, so we know that each of the sides is n, but then we each have an extra 1. Each n has an extra 1. So let's look at the red line. The red line would be n plus 1. The purple line would also be n and then 1 more. The black line would be n plus 1 more. And then the blue line would also be n plus 1 more. So we have 4 groups of n plus 1. All right, let's keep going. Again, so we've already talked about equivalent expressions are expressions that are equal for any value of the variable. Meaning, if you plug in a number to these expressions, they would be equal. So let's do that for Kyrie and Manuel's expressions. Kyrie's was 4 times n plus 1. Let's put in a 2 for n. 2 plus 1 is 3. 4 times 3 equals 12. Let's put in a 2 for each of the ends here. 2 plus 2 is 4. 2 plus 2 is 4. Plus 2. plus 2 also equals 12. So these two expressions, they mean the same thing. They have equal values, except they just look different. Kyrie and Manuel pictured things differently, and that is okay. Oh, I didn't even read the question. Use it to calculate when n equals 8. So if you plugged in an 8, also you would get the same thing. All right, let's keep moving along. So we just used a 2 instead of an 8. Which expression is also equivalent to Kyrie's and Manuel's expression? All right, let's try to figure this out. So we've already talked about how each side length of the square is n, and then we have 4 additional units. So let's talk about our n's. We have 4 of them. So we have 4 n's, and then we have the corners, which is 4. All those ones also equal 4. So our expression could be equal to 4 n's and then plus 4. So that would be option C. Again, each side of the square is n. They are all the same because it's a square. And then we have 4 additional squares that are each the same length. Or same size, I should say, that are each 1 unit. So we have 4 n's plus 4 other units. All right, let's keep going. How do these diagrams show 4n plus 4 and 4 times n plus 1? So the first one is very clear, 4n plus 4. We have 4 n's, and then we also have 4 units. So that's where the 4n plus 4 comes from. Now let's look at 4 times n plus 1. Remember, this means multiplication in between the 4 and the n plus 1. We have n plus 1, and we have 4 groups of it. Look at each n plus 1. 1, 2, 3, 4 n plus 1s, and so we have 4 groups of n plus 1. So that is where the 4 times n plus 1 comes from. All right, let's keep going. Match each expression with the diagram it represents. One expression will not have a match. All right, let's look at the first group over here. We have n's, and we have 3 of them. And then we have 1's, and we also have 3 of them. So first let's look. Do we see anything that says 3 n's plus 3 more? Yes, we do. All right. We can also look for, we have 3 groups of n plus 1, which would be right here. 3 groups of n plus 1. One, 2, 3 groups of n plus 1. So we have 3 n's plus 3 different units, which in other words is 3 groups of n plus 1. All right, let's look at the next one now. We have 3 n's, and then we have 6 1-tiles. So that's going to be 3n plus 6. Hold on, I'm going to make this look a little less confusing. Again, so we have 3 n's and then plus 6 units. We also, so each group here is n plus 2. So let's look. Do we see something that says 3 groups of n plus 2? And we do right here. We have, so we have n plus 2 plus n plus 2 plus n plus 2. That is 3 groups of n plus 2. So we have now used that. We've used 3n plus 6, 3n plus 3, and 3 times n plus 3. And then it said that one will not have a match, so we have matched them all. All right, let's keep going. Write an expression to represent this new diagram. Try to write an expression that none of your classmates will. We're going to look at the n's and we're going to look at the ones. We have 6 n's and we have 3 ones. So our first expression could be 6n plus 3, because we have 6 n's and we have 3 ones. Now let's also look at our groups. We have 3 different groups, and they are each 2n plus 1. So we have 2n's plus 1 3 different times. So 2n plus 1, and then multiply that by 3. We could also write this as 2n plus 1 3 different times. Because again, we have 3 groups of 2n plus 1. All 3 of these expressions are equivalent. All right, let's keep moving. All right, so again, today we have discussed when expressions are equivalent or mean the same thing, but just look different. If you plug in a variable, they will equal the same thing. They represent the same diagram, just in a different way. But they are still equal and can both be used. All right, so we are now done with the lesson and we will move on from here. All right, bye guys, have a nice day.